All right, this is what I was trying to make an improvement on. This is a heater core from an automobile, and it is called a tube and fin. And when you get real close, if it'll focus, you can see the fin part, the real thin parts, as they attach to the tube, which is the wider steel parts, have only a point contact, a very small point contact, maybe 1 millimeter wide, but then they go through the thickness of it in order to get as much contact on that tube as they can. I said, well, what if I was to take a solid piece of aluminum, and I'm going to get out a piece here, and I put it on that, and I make it to where these fins are and this part of the fin is the contact, so that I would have an area of a much bigger area, surface area. So then, now I designed this extrusion in such a way that it will, when they're cut in lengths, they have a the way they're extruded is so they will nest together, and they will form a combination where they fit together. I like to call it the dragon tooth, because it looks like teeth. Looks like teeth of a dragon. But anyway, they fit together so let's say some kind of a fluid will go through the part here. They'll go through this part here, and then when another one of these, let's say, is put on this side here, then it could have even a gap in between where another fluid, of course it would have to be welded with another material here to connect it together. But then when this would have a gap between, then let's say a fluid, let's say like the coolant of an automobile engine, let's say, or cooling of an engine would go through, it would have this entire surface area for contact to dissipate its heat into the aluminum. Aluminum is a very good conductor of heat, so it would heat sink it into it. So now this thing here is hot, so then when another fluid through here, let's say it's air or a gas or whatever, and you're blowing air through this, then it was has all this surface area of all these air things all the way down full length, or however long you want to make the thing, in order to absorb the heat into the gas. And at some part farther down the line, you would have a fan extracting that heat. So the amount of surface area of here is many, I don't know how you calculate it, do it by math, whatever, has much more surface area for the whole unit than just the point-to-point contact of just the little tubes here. So when you put this all together, it would probably be possible to have, let's say, the cooling capacity of this size here could be a much smaller total size. Now the weight of the aluminum, of course, is a factor value-wise, but the efficiency could be such that it would be more than compensate for the size of the radiator that you're going to be making. And one of my calculations was I could take the size of an automobile radiator, let's say that goes in a large truck, let's say my truck over here, and let me just go over here and, well, I'll have to show later because I don't have my keys. But anyway, they have multiple radiators stacked in front of each other. They've got the air conditioning radiator, they've got the oil cooling radiator, they've got the engine fluid radiator, plus transmission fluid line radiator things. And so they got all these things trying to dump their heat into the air. So they got them all stacked together. And you can go look at just about any of these trucks and you'll see these radiators all stacked together. They're trying to dump their heat into the atmosphere. So then I said, well, what if you were to take one of these units here, whatever length you need, and then make different channels. One channel for the engine, another channel for the transmission, the air conditioning. Each one would have a different path, and that could be, the flow could be lengthways, or it could be engineered to where it would go in a back and forth. In other words, let's say it would go from entering to one end here, and then it would go, focus here, then it would go in a serpentine way, enter in this end, and then of course let's say these two sides are blocked, but then we go in this end and go through this long serpentine path, and then finally exit out this end, and the amount of heat from that area would be all into the now aluminum, so that when another surface is presented, then that amount of heat can now be dissipated. Now this is in the air that's blown by, so then now you can dissipate into the air. So that is the basic premise of this patent. I've got it into a real world example now. Now what's interesting, I'm out here in a hot blazing sun, and it's a nice warm day. I put my hand on here, just another observation. This thing is cool to the touch. It actually feels quite cool, but I touched the hot black stuff. I mean, it's hot enough where, let's just say it's uncomfortable to hold on to it temperature wise, but yet just for craziness, the way it sits here in the sunlight, it's actually cool to the touch. So this application could be not just for fluids, it could be like for cooling, let's say LED lights, laser beam lights, all kinds of different electronic stuff that could be mounted to the surface of this, and then cooling refrigerant air or whatever would be blowing through to cool it, like say a chilled liquid. And then on the surface of this you'd be mounting your whatever you want to cool. And so the gaming industry, like when they want to overclock and run their games on these hot rodded CPUs, the CPUs have to dump their heat, and there's a lot of different water cooled gaming devices, or things out there, and they somewhat look like one of these. Only you'll see them. They have little fans on them, and they got the chips mounted and stuff. But this could be used in the same manner for overclocking their CPUs. So anyway, this was just a basic idea and an observation of conversion of my patent. That's US 7588074, and converting that to a real world hands-on device. Thank you. We'll see you in the next video. Bye.